Hello friends, I am Dr. Gaurav. In this video, I will discuss about Carnot cycle, reverse Carnot cycle and their limitations. Contents are Carnot cycle, reverse Carnot cycle, limitations of Carnot cycle and reverse Carnot cycle. First is Carnot cycle. Probably the best known reversible cycle is the Carnot cycle, first proposed in 1824 by French engineer Sadi Carnot. The Carnot cycle is composed of four reversible processes. First is reversible isothermal expansion process 1-2. In this, temperature is constant, so TH is constant, that is T1 is equal to T2 is equal to TH. Amount of heat supplied by energy source at temperature TH is given as QH is equal to P1 V1 natural log V2 by V1 is equal to M RG TH natural log V2 by V1. We know that ideal gas equation is PV equal to M RG T. Here P represents pressure, V represent volume, M represent mass, RG represent gas constant, TH represent temperature at the energy source. You can see the diagram. In this diagram we are having cylinder and piston. Now from energy source at temperature TH we are supplying QH amount of heat in the cylinder in such a way the temperature remains constant and the piston will move from position 1 to 2. You can see the PV diagram. In this PV diagram 1 2 process represent reversible isothermal process and we are supplying QH amount of heat from energy source at temperature TH. In the TH diagram, that is temperature entropy diagram, the process 1 2 again represents reversible isothermal process. So it is represented with the horizontal line. That means T1 is equal to T2 is equal to TH and we are supplying QH amount of heat from energy source at temperature TH. Second process is reversible adiabatic expansion or isentropic expansion process 2-3. Temperature drops from TH to TL because it is a expansion process, and in isentropic expansion process the amount of heat transfer is 0. You can see the diagram. In this diagram cylinder is insulated, so there will be no heat transfer and the piston is moving from position 2 to 3. So it will represent expansion as the volume is increasing, and due to this expansion temperature drops from TH to TL. In the PV diagram the process 2-3 represent reversible isentropic expansion process as the volume at point 3 is more than that of the volume at point 2. So it is an expansion process. In the TH diagram, the process 2-3 is represented by vertical lines. That means S2 is equal to S3. Entropy at point 2 is equal to entropy at point 3. So this is a reversible isentropic expansion process, or we can say isentropic expansion process. Next is reversible isothermal compression process 3-4. TL is constant, that is T3 is equal to T4 is equal to TL. Amount of heat jetted to energy sink at temperature TL is given as QL is equal to P3 V3 natural log V3 by V4 is equal to M RG TL natural log V3 by V4. If you see the equation of QH and QL, now we want to have a relation between V2 upon V1 and V3 upon V4. So we will use the process 2-3, which is isentropic expansion. That is T3 by T2 is equal to TL by TH is equal to V2 by V3 whole raised to power gamma minus 1, where gamma represent isentropic index. Process 4-1 is isentropic compression. So we will have a relation T4 by T1 is equal to TL by TH is equal to V1 by V4 whole raised to power gamma minus 1. When you compare both these equations, we will get V2 by V3 is equal to V1 by V4, or we can say V2 by V1 is equal to V3 by V4. That means we can replace this V3 by V4 with V2 by V1. So the value of QL comes out to be P3 V3 natural log V2 by V1, or mRG TL natural log V2 by V1. You can see the diagram C, in which the process is 3-4. Now the piston is moving from position 3 to 4. In this movement, it is rejecting heat having a value of QL to the energy sink at temperature TL, keeping the temperature constant. As the volume is decreasing from 3 to 4, so it is a compression process. In the PV diagram, 3-4 represent reversible isothermal compression process, in which QL amount of heat is rejected to the energy sink at temperature TL. In the TS diagram, 3-4 is the reversible isothermal compression process. So it is represented by a horizontal line. That means T3 is equal to T4 is equal to TL, and it is rejecting QL amount of heat to the energy sink at temperature TL. Next process is reversible adiabatic compression or isentropic compression. Process 4-1. Temperature rises from TL to TH because it is a compression process, and in this case the value of heat transfer is 0. You can see the figure D. In this process 4-1 represent reversible adiabatic compression or isentropic compression. As piston is moving from 4 to 1, there is a compression, so there will be increase of temperature from TL to TH, and the cylinder is insulated. That means there will be no heat transfer. In the PV diagram, 4-1 represent reversible adiabatic compression or isentropic compression process, as the volume is decreasing from V4 to V1. In the TS diagram, vertical line 4-1 represent reversible adiabatic compression or isentropic compression process, because entropy at point 4 is equal to entropy at point 1. The theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine. It is a hypothetical heat engine. Assumptions made for describing the working of the Carnot engine are as follows. The piston moving in a cylinder does not develop any friction during motion. The wall of piston and cylinder are considered as perfect insulators of heat. The cylinder head is so arranged that it can be a perfect conductor in case of isothermal process, or perfect heat insulator in case of isentropic process. The transfer of heat does not affect the temperature of source or sink, that is TH and TL. Working medium is a perfect gas and has constant specific heat. Compression and expansion are reversible. The thermal efficiency of any engine, reversible or irreversible, is given as the ratio of desired work output divided by required heat input. So W net divided by Q in. We can replace this W net in terms of heat as Q in minus Q out divided by Q in. So we can write down this one as 1 minus Q out divided by Q in. And Q out is the amount of heat ejected to the sink, that is QL, and Q in is the amount of heat supplied, that is QH. So for Carnot heat engine, we have already find the value of QL and QH. This is the value of QH and this is the value of QL. So putting the value of QH and QL in this equation and cancelling the common terms, we will get the final relation as 1 minus TL divided by TH, where TL is the temperature of energy sink and TH is the temperature of energy source, or we can say in this way 1 minus lower temperature divided by higher temperature. Hence, efficiency of Carnot heat engine is independent of working fluid and depends upon the temperature of source and sink. From this equation, it is proved that it is independent of working fluid. It depends only on the temperature of source and sink. If the value of TL is 0, that means efficiency is 1, or we can say efficiency is 100%. However, that means absence of heat sink, which is a violation of Kelvin-Planck statement of second law, which says that efficiency of heat engine cannot be 100%. Being a reversible cycle, the Carnot cycle is the most efficient cycle operating between two specified temperature limits. It means that whatever efficiency we will get from Carnot's heat engine, it will be the maximum efficiency. Next is reverse Carnot cycle. The Carnot heat engine cycle just described is totally reversible cycle. Therefore, all the processes that comprise it can be reversed, in which case it becomes the reverse Carnot heat engine. Carnot refrigerator and Carnot heat pump works on reverse Carnot cycle. The reverse Carnot cycle is composed of four reversible processes. First is reversible adiabatic expansion or isentropic expansion. Process 1-2. Temperature drops from TH to TL and the value of heat transfer will be 0. You can see the PV diagram. 1-2 process represent reversible adiabatic expansion as the volume is increasing from 1 to 2, or we can say isentropic expansion process. In the TS diagram, you can see 1-2 line is vertical line, that means entropy is same, S1 is equal to S2. Next is reversible isothermal expansion process 2-3. TL is constant, that is T2 is equal to T3 equal to TL. Amount of heat removed from low temperature reservoir which is at temperature of TL. So value of heat in this case QL is equal to P2 V2 natural log V3 by V2, or we can say M RG TL natural log V3 by V2. This process 2-3 represent reversible isothermal expansion process as the volume is increasing from 2 to 3, and QL is the amount of heat extracted from the low temperature reservoir which having temperature value TL. In the TS diagram, you can see 2-3 is represented by a horizontal line, that means T2 is equal to T3 equal to TL. Next is reversible adiabatic compression or isentropic compression process 3-4. Temperature rises from TL to TH. as in case of compression the temperature increases, but value of heat transfer is 0 because it is an isentropic process. This 3-4 represent reversible adiabatic compression or isentropic compression as the volume is increasing from 3 to 4. In the TS diagram you can see 3 to 4 is a vertical line, that means entropy at point 3 is equal to entropy at point 4. Next is reversible isothermal compression process 4-1. Th is constant, that is T4 is equal to T1 is equal to Th. Amount of heat supplied to high temperature reservoir at temperature of Th is given as P4 V4 natural log V4 by V1 is equal to M Rg Th natural log V4 by V1. You can see the PV diagram. 4-1 represent the reversible isothermal expansion process and QH is the amount of heat supplied to the high temperature reservoir at temperature Th. In the Th diagram you can see 4-1 is represented by horizontal line, that means T1 is equal to T4 is equal to Th, and QH is the amount of heat rejected to the high temperature reservoir at temperature Th. So remember QH is the amount of heat supplied or we can rejected to the high temperature reservoir at temperature Th. Now if you see the equation of QL and QH, now we want to find out a relation between V3 by V2 and V4 by V1. This can be find out with the following relations. For process 1 2 we are having isentropic expansion, so the relation will be T2 by T1 is equal to TL by TH is equal to V1 by V2 whole raised to power gamma minus 1, where gamma is isentropic index. For process 3-4 it is a isentropic compression. T3 by T4 is equal to TL by TH is equal to V4 by V3 whole raised to power gamma minus 1. If we compare both the relation, we will get V1 by V2 is equal to V4 by V3, or we can say V4 by V1 is equal to V3 by V2. Now you can replace this V4 by V1 with V3 by V2. So the value of QH will be P4 V4 natural log V3 by V2 is equal to M Rg Th natural log V3 by V2. For Carnot refrigerator we will have COP, note efficiency. In case of refrigerator and pump we always use COP. So the formula of COP is output upon input, and what is the output? In this case output is QL, that is the amount of heat extracted from low temperature reservoir, and input is W net in. We can replace this W net in with heat in the form QH minus QL. Now we have the value of QL and QH. If we put the value and cancel the common terms, the final answer is TL divided by TH minus TL. TL is the temperature of low temperature reservoir, and TH is the temperature of high temperature reservoir, or we can say lower temperature divided by higher temperature minus lower temperature. For Carnot heat pump, COP is output upon input, that is QH divided by W net in, where Q is the amount of heat rejected to the high temperature reservoir. So we will have QH divided by QH minus QL. Cancel the common terms, but we get TH divided by TH minus TL. So we can say higher temperature divided by higher temperature minus lower temperature, where TH represents temperature of high temperature reservoir and TL represents the temperature of low temperature reservoir. Hence, COP of Carnot refrigerator and heat pump is independent of working fluid, that is refrigerant, and depends upon the temperature of source and sink. As we are having only temperature ratios. Next, we have taken an example for Carnot heat engine. Let us assume that we are having a value of TH, that is temperature of source, equal to 600 Kelvin, and temperature of sink TL sink is TL is equal to 300 Kelvin, and rate of heat supplied to the engine from the source is equal to 10 kilowatt. From these values we will find out the value of efficiency. So efficiency is TH minus TL divided by TH. The answer will be 0.5. Now if in terms of heat, the formula of efficiency is 0.5 is equal to rate of heat supplied to the engine minus rate of heat rejected to the sink divided by rate of heat supplied from the sink from source to the engine. Now it is given that rate of heat supplied from the source to the engine is 10 kilowatt. So you can find out the value of rate of heat rejected to the sink, and it comes out to be 5 kilowatt. So the amount or rate of work done by the engine, that is output, is equal to 10 minus 5 is equal to 5 kilowatt. Now we know that this is the maximum work we can get from any engine, any heat engine. So you can see the first diagram here. This is the value of 5 kilowatt we are getting. So we are saying this is the ideal but possible. This is the maximum amount of work done we can get from a engine in which source temperature is 600 Kelvin, sink temperature is 300 Kelvin, and the amount of heat supplied from the source is 10 kilowatt. This is the best that can happen. Next is, if we are getting a work output of 3 kilowatt and rejecting the heat to the sink 7 kilowatt, keeping the initial condition same, this is real and possible. What happens to our practical systems? Next is, if we are getting a work output of 6 kilowatt and rejecting a heat of 4 kilowatt to the sink. This is not possible because we are getting output more than that of the efficiency of Carnot heat engine. So it is not possible. Maximum we can have is the Carnot efficiency. Next example is for Carnot heat pump. Suppose the given conditions are value of TH, that is high temperature reservoir, is 303.15 Kelvin, and the value of low temperature reservoir is TL is equal to 253.15 Kelvin, and the amount of heat extracted from the low temperature reservoir is 10 kilowatt. We know that COP of Carnot heat pump is given as TH divided by TH minus TL. Putting the value of TH and TL, we will get COP of Carnot heat pump as 6.063, and in terms of heat we can write down COP as 6.063 is equal to rate of heat supplied to the high temperature reservoir divided by rate of heat supplied to the high temperature reservoir minus rate of heat extracted from the low temperature reservoir. Now the value of rate of heat extracted from low temperature reservoir is given as 10 kilowatt. So the answer comes out to be for amount of heat rejected to the high temperature reservoir as 11.975 kilowatt. Now if you want to find out the work input to the system, it comes out to be 11.975 minus 10, that is 1.975 kilowatt. What is the meaning of this work? This is the minimum amount of work which is supplied to the as input to the Carnot heat pump, so that we can extract heat having value of 10 kilowatt from low temperature reservoir at temperature of 253.515 Kelvin, and supplying the heat to a high temperature reservoir at a temperature of 303.15 Kelvin. So, to extract this 10 kilowatt of heat for the given temperatures TH and TL, we need to supply minimum amount of work, that is 1.975 kilowatt. If we supply work less than this value, then it will not extract 10 kilowatt of heat from low temperature reservoir. So this is the minimum value we need to supply. So you can see in the first figure, you can see ideally but possible, this is the best that can happen. In the second, we are supplying the value of work 3 kilowatt, which is more than that of the 1.975 kilowatt. So this is real and possible, and this is what happens in reality. But if you supply value of work less than 1.975 kilowatt, that is 1 kilowatt, then this type of heat pump is not possible. Next is limitations of Carnot cycle and reverse Carnot cycle. Even though the Carnot cycle or reverse Carnot cycle cannot be achieved in reality, the efficiency or COP of actual cycle can be improved by attempting to approximate the Carnot cycle or reverse Carnot cycle more closely. Reason for impracticability are all the four processes have to be reversible. It is impossible to perform a frictionless process. So whenever there is a friction, then the process cannot be reversible. Next point is the heat absorption and rejection take place with infinitely small temperature difference. It is impossible to transfer the heat without temperature potential. As we are saying, we are supplying heat keeping the temperature constant in case of isothermal process. Third point is isothermal process can be achieved only if the piston moves very slowly to allow heat transfer so that the temperature remains constant, as we have done for the process in case of Carnot cycle 1, 2 and 3, 4. Adiabatic process can be achieved only if the piston moves as fast as possible so that the heat transfer is negligible due to very short time available, as we have done for the process 2, 3 and 4, 1. The isothermal and adiabatic process takes place during the same stroke, that is 1, 2, 2, 3. It is one stroke, 1, 2 and 2, 3. In case of Carnot cycle, I am taking the example of Carnot cycle. Therefore, the piston has to move very slowly for the part of the stroke, that is from 1 to 2, and it has to move very fast during the remaining stroke, that is 2 to 3. This variation of motion of the piston during the same stroke is not possible. Thanks. Any questions you can write to me gaurav.citem@gmail.com.